this is a nice paper that looks at how the cyclones are beginning to increase their intensification as they approach the shores. We talked about rapid intensification where the wind speeds, maximum sustained wind speeds, jump by more than 55 kilometers per hour within a 24-hour period. Makes it difficult to predict, and then it always obviously scares people, because if it suddenly accelerates and becomes stronger, accelerates is the wrong word, suddenly it becomes stronger, then of course it could bring much more damage, much more rain. And if it increases its intensity near shore, then it will bring even more water, storm surge, inundation, wind damage, and rainfall, right? So this is clearly something to worry about. This lead author has published several papers on cyclones, various aspects of ocean impacts, etc. Tropical cyclones inflict substantial coastal damages, making it pertinent to understand changing storm characteristics in the important nearshore region. Past work examined several aspects of TCs relevant for impacts in coastal regions. However, few studies explored nearshore storm intensification and its response to climate change at the global scale. Here we address this using a suite of observations and numerical model simulations. Over a historical period of 1979 to 2020, observations reveal a global mean TC intensification rate increase of about 3 knots per 24-hour in regions close to the coast. An analysis of the observed large-scale environment shows that stronger decreases in vertical wind shear and larger increases in relative humidity relative to the open ocean are responsible. So there are specific causes which are driving these, which is very important, because then predictions can be looked at in terms of how the models are doing the vertical wind shear and relative humidity. Further high resolution climate model simulations suggest that nearshore TC intensification will continue to rise under global warming. Idealized numerical experiments with an intermediate complexity model reveal that decreasing shear near coastlines driven by amplified warming in the upper troposphere and changes in heating patterns is the major pathway for these projected increases in nearshore TC intensification. So obviously if this is happening, then you want to see if this will continue into the future, so that's why projections are made, but you have to be, there is a caveat associated with that, which I will explain with the figure. What is the plain language summary? I want to read it just in case you are not an expert on cyclones. Tropical cyclones that intensify close to the coast pose a major socio-economic threat and are a substantial challenge from an operational standpoint. Therefore, understanding historical trends in nearshore storm intensification and how they may change in future is of considerable significance. Despite this, few studies examined this key aspect of TCs at the global scale. Here we show, using an analysis of observations and atmospheric analysis, that the mean TC intensification rate has increased significantly over the period of 1979 to 2020, primarily aided by increases in relative humidity and decreases in vertical wind shear, which is the way winds change from the surface into the atmosphere. Further high-resolution climate models which explicitly resolve TCs suggest that nearshore intensification will continue to increase in the future. So this is important. If you want to say something about the future, then you have to have an actual TC resolving model, but there are still some caveats which we'll see. These increases in coastal TC intensification rates can mainly be attributed to stronger projected decreases in vertical wind shear. To better understand wind shear projections, a suite of idealized numerical experiments with an intermediate complexity model were conducted. The experiments indicate that enhanced warming in the upper troposphere and changing heating patterns are likely responsible. So you are switching between several models. A reduced complexity model will allow you to make more experiments, but then the results have to be interpreted carefully as well. Okay, so run through some figures. So this is the near shore TC track locations used in this analysis. obviously all the major coasts of cyclone impacts are considered, and you can see that the intensification rate in knots per 6-hour period are looked at for the rates. So less than 7.5, less than minus 7.5, so they will be decreasing, minus 7.5 to 0, 0 to 7.5 knots per 6-hour period, and greater than 7.5. So this is near shore intensification rate, and the periods looked at in the orangish colors, 2000 to 2020, 1.15 knot per 6-hour period. So you can look at the number of samples so that statistical significance is guaranteed, and 1979 to 1999. So you can see that there is a decrease in intensification, or a minus 7.5 to 0, which means there is no diminishing happening. Typically the cyclone approaches land, part of it begins to hit the land, and energy source is from the ocean. So you expect it to begin to slow down or weaken, which is what this would have implied. But instead now you are having increases in the 0 to 7.5 and greater than 7.5 knots per 6-hour period as well, and the difference is again significant of the pre 99 and post 90, post 99 or post 2000 period. Okay, so there has been argued to be a regime. There is an argument that a regime shift happened around this period. 1998, 99 was a big El Nino, and then La Ninas followed, and then the global warming pattern has also remained La Nina like. There are all these details, but a regime shift is noted by several studies. So observed changes in the mean nearshore and offshore TC intensification rates for major coastlines of the world and for the 42-year period of 1979 to 2020. This is just reinforcing the regional amplifications as well. So offshore intensification has decreased, and for the US and Gulf Coast you can see a positive number. Mexican coast has seen a reduction, East Asian coast has seen an increase, South Asian coast has seen an increase, South African coast and Australian coast. Of course, the bold numbers are statistically significant and others are not. That depends on various factors. Okay. So important that it's happening along most coasts, and there are details as to why there are differences in the coasts. Again, goes back to relative humidity and vertical shear. This is the spatial pattern of trends in SST. We know this is warming and significant. There is warming. This is a major typhoon generation area. More than 30% of the total cyclones are generated here, and of course this is a very active hurricane generation as well, and there are smaller regions elsewhere as well. So this is the relative humidity trend. So you can see a decrease here, decrease here, and decrease here, decrease here, and so on, and shear has decreased as well. So just these are the major factors that can contribute to cyclone genesis as well as the intensification of the cyclone. Remember that energy for the cyclones comes from the oceans. It's not always SST, it's the heat content, but as you come close to the shore, the SST, it's shallower, it can be well mixed, so SST and heat content can be much closer to each other than in a deeper ocean. Here are the numbers again for coastal and offshore warming trends over this period. Both have shown warming, but coastal trends show somewhat of a higher trend. The vertical wind shear has shown a decrease. Is there a real significant difference between coastal and open ocean, offshore? Not clear, but in the relative humidity you see a clear difference. There is an increase in relative humidity in the coastal regions than in the offshore regions. Okay, so nearshore TC track locations used in this analysis. These are the probability distributions of 24-hour TC intensification rates for the historical period of 1979 to 2014, and then 2015 to 2050, when the study was done, what historical period was used, what was the projection period. That's what is being said here. So you can see that's the blue, and so this is the differences. So 2015 to 2050 is shown in orangish colors, and 1979 to 2014 are shown in bluish colors, and the message is same, that the offshore diminishing is more prominent, and then you get increases in offshore intensification, and here the various bins. So 0 to 2.5 knots per 6 hour period, 2.5 to 5, and then smaller numbers in the tails. Okay, even the tails may matter, because the jump in wind speed can mean quite a serious increase in the damages, especially if people keep moving closer to the coasts and so on and so forth. So I'm not reading all the details, because the main message is fairly clear. And I want you to focus on that. And if you want details, obviously you have to read the paper, which is a nice and long paper actually, with lots of details. Projected changes in the mean nearshore and offshore intensification rates for major coastlines of the world, and for the 72-year period of 1979 to 2050. So again, the message is similar, that intensification of cyclones near shore will increase, but you have to be clear that projections have a lot of uncertainties. Even when you use high resolution models, but with forced sea surface temperatures from some models with projections, there are lots of biases and uncertainties in the models, and the global models that are often used to give the sea surface temperature information for the future don't explicitly resolve cyclones, but here if you use a high-res MIP, which does permit cyclone resolution, doesn't mean it's a cyclone prediction model. It's just that it has high enough resolution to produce cyclones. Okay, so all those caveats have to be kept in mind. But what is the risk? If you are getting more and more people moving closer to the shore, and you have sea level rise happening, then you have to really worry about the risk of near shore intensification of cyclones, and then how the cyclone numbers are increasing as well, right? Or if numbers are not increasing, which seems to be the case on a global level, how the stronger category cyclone number is increasing. So total number of cyclones may remain same, but you can get more number of stronger category cyclones, which will intensify near shore, then create lots of problems, right? So this is the more details on the vertical wind shear changes projected by 15 CMIP6 models. These are full on coupled models at lower resolution. They do not resolve cyclones, so you obviously have to be careful. Vertical wind shear change by the SWM, which is the stationary wave model. So you want to also see, so these are basically taking the output from these models to drive wave models, which are run at much higher resolutions, and so on. So all those translations can amplify uncertainties and biases that are in there, but I don't want to add seeds of doubt. I just want you to focus on the risk of cyclones increasingly intensifying as they approach the shore, right? VWS response, so vertical wind shear response to basic states, transient forcing. So that's about how increasing CO2 and the warming will give you the forcing increasing with time, as opposed to just fixing a future state and a current state and comparing the two states. Details, if you want, you can read up, but they are not so critical for your understanding. The results from our study have profound implications for populations living in coastal regions, operational forecasters and decision makers under global warming. A heightened nearshore intensification rate implies a potential strengthening of landfalling tropical cyclones. destructive tropical cyclones' destructive capacity, primarily determined by their maximum intensity and inner core precipitation. Changes in these factors are closely associated with intensification rate of TCs within coastal regions. The stronger winds and heavier precipitation produced by landfalling TCs can exacerbate the impacts of storm surge and increase the risk of coastal flooding. Combined with anticipated growth of coastal population and wealth, TCs striking coastal areas are likely to result in more substantial economic losses, fatalities, and property damages during the 21st century. This is a risk that we have to prepare for, keeping in mind that there are limited resources, so you will also need much more local information as to where this is likely to happen and most likely to happen, so that you cannot strengthen all the shores, so you have to optimize resources as well. In our study, we only considered the coastlines of major continental land masses affected by TCs as near shore. However, several island regions across the world remain vulnerable to the disastrous effects of landfalling TCs. For instance, an examination of observed TC data for the Philippines and Madagascar indicates that the mean nearshore TC intensification rates may also have increased for those regions, which is shown in the supplementary material you can follow up with. Future studies focusing on changing nearshore TC intensification for such regions, including the responsible mechanisms, are needed. Again, this repeats how examining the large-scale circulation changes is split into vertical wind shear decreasing, which allows the intensification of the cycle. Vertical wind shear tends to chop off the cyclone, take away the energy, weaken it, and so on. But if you weaken the vertical shear, then the cyclone can keep intensifying and growing. And there are details as to what the US coast is doing and other coasts are doing, and so on. And of course, there are also details on how region-specific relative humidities are changing. The wave model experiments reveal that primary factor responsible for reducing shear over Northeast Asia is the enhanced tropical upper level warming. This is a response to global warming as well. Additionally, interbasin changes in diabatic heating, which means heating coming from condensation of water vapor, are shown to play a critical role in contributing to the weakened vertical shear along the US coastlines. So there are region-specific processes as well. Satellite measurements have revealed that upper atmosphere has been warming at a faster rate than the surface since 2000. So there is some information and analysis of why that happens. And the observed tropical tropospheric temperature trends have been accurately captured by the current CMIP-6 models. So even though they don't resolve cyclones, they have captured this response of the large scale. The faster warming in the tropical upper atmosphere is expected to continue during the 21st century and is regarded as a robust climate projection across different models. Therefore, to improve our confidence in future VWS projections, it's essential to understand the uncertainty of projected heating trends, which is closely related to the intermodal spread in SST warming pattern. This is a complicated statement, but basically there is, we are increasing greenhouse gases causing global warming, but there are regional patterns of how the response evolves. I mentioned La Nina-like response, which means the East Pacific is not, Eastern tropical Pacific is not warming or maybe even cooling, while the Western Pacific is, and so on. And there are other regions on land that are warming fast as well, like the Mediterranean and the Middle East. All these together determine how the circulation changes, which we call the dynamic response. And then there is a heating response, which is the thermodynamics of how the atmosphere is picking up moisture and where it's forming clouds and rain and so on and so forth. Okay. Although the potential for so previously CMIP-5 models did not have consensus regarding an El Nino-like warming pattern in the future, although the potential for enhanced future warming in the Eastern Pacific has emerged more clearly in the CMIP-6 multimodal ensemble, considerable intermodal spread remains. Further work is needed to reduce uncertainty. So there are nice papers from Richard Seeger and so on showing that the models are actually not doing very well in projecting Eastern Pacific warming trends or cooling trends. So this is critical because that has a big role to play in how much heat will go into the ocean, how the El Nino will respond because it's in a critical region. But we have discussed that elsewhere, so I won't go into the details here, but just keep that in mind. Models always have uncertainties, and there are details on how the uncertainties are affected in the beginning, like next 10 to 20 years, which is what they are considering here, versus the later decades. But again, coming back to risk, you always have to focus on the potential risk and what you can do about it, considering the limited resources. Okay, so I will leave it here. Nice paper. Please follow up, read the details if you are interested. Okay.